So we got everything going. So you can see my lovely face as I'm going through this lovely, lovely section 1 lesson for you. So just kind of how this is today is going to go. We'll do a PowerPoint today. This is obviously isn't going to be how things go every single time, but today, really, why not? We're in day 2. Let's do a PowerPoint presentation. So those of you who are online are getting exactly the same thing that are getting that are kind of here. So yeah, so let's kind of get going. Basic concepts. I'll put the PowerPoint up as well, so you guys can read. So I'm just going to kind of go beyond what the basic concepts are here. So our first objective today is we're going to write sets using set notation. And that's kind of the key in here today is what is that set notation and what does set notation look like. So a set is a collection of objects that we call elements or members of those different sets. So in algebra, elements of sets are usually put inside of brackets. And we use these brackets right here to enclose those different elements. Numbers is really what elements are. Okay, so for example, let's say that we have the set of numbers 1, 2, 3, 4, 5, 6. These are actually what are called the natural numbers, and that's kind of terminology that we're going to talk about a bit today too, is different types of numbers. The natural numbers are kind of what we call our counting numbers. So you'll see that we have the set n is 1, 2, 3, 4, 5, 6, and then a bunch of dots. Well, in mathematics, those 3 dots means that those numbers are going to continue to go on in that same pattern that has been developed kind of indefinitely. So really becomes what we call kind of an infinite set. You can put the dots out in front as well, which you'll see a little bit later. But that's kind of what we call the natural numbers. It's kind of your counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. When you include 0 in to the set of natural numbers, we have what's called the whole numbers. So the whole numbers, so there's your natural numbers plus the dots. To get the whole numbers, you add a 0 in there. So that's all of what we consider to be the whole numbers. And these are just different sets. We have the set of natural numbers, we have the set of whole numbers. There's also a set that has no elements. That's what we call the empty set. The empty set is either denoted with a circle with a slash through it, or just kind of empty brackets is how we represent what we call an empty set. There's nothing within that set of things. This part of it we're not going to worry about. So when we're talking about sets, order really doesn't matter when we're talking about sets. So this set 1, 2 is equivalent to the set 2, 1. Order doesn't necessarily matter. Now we'll say that we always want you to kind of go in ascending order from least to greatest, but you don't have to. But it's nice to me if you do that. That way I can just read it and I don't have to search for numbers. But again, order doesn't really matter when you're doing these. If you see an equal sign with a slash through it, that means the sets are not equal to each other. Since 0, 1, 2, and then you have the set 1, 2, since 0 isn't in the second set, then they don't match each other. So they're not equal to each other. Of course, then we can also put variables inside of things. Variables are just often used to represent numbers or sets of numbers. So for example, x, that mark, x is the natural numbers between 3 and 15. That reads that the set of all elements x such that x is a natural number between 3 and 15. Now, we could write that set out as the set of 4, 5, 6, ... means continue that pattern until you get to 14. But you can put variables in there kind of as well. This is what we call set builder notation. We're not going to worry about set builder notation too much other than to kind of give you the definitions kind of here. What this kind of means and how this reads is the brackets mean the set of all elements x. Green is such that x is the given property. So that's what we call set builder notation. We're not going to worry about set builder notation really a whole lot. But what we do want to be able to do is we want to be able to list the elements that are inside of something that's in set builder notation. So this is in set builder notation. and we want to list the elements. So we're going to list the set of the elements such that x is a natural number greater than 12. So if it's a natural number greater than 12, the numbers start at 12, and the natural numbers just increase by 1, and they continue in that pattern for infinity. So we call that the natural set of numbers greater than 12. Okay. Oh, sorry, it was greater than 12. I actually messed up, so I shouldn't have used 12. Greater than 12, 12 is not there, so I should have used 13, 14, 15. Sorry about that. My bad. It happens. I'm not going to start the video over when I make mistakes. It's just be too much to do. Use set builder notation. I said we're not going to do that, so we're not going to do that. So that's the first thing, putting things in elements of different types of sets. Second part, use of number lines. You guys know how to use number lines, so we're going to make this quite quick. The left-hand side is your negative numbers. The right-hand side is your positive numbers. 0, of course, is either positive or negative. Here becomes a set of all numbers. Any number on the number line is considered to be an integer. I often say that integers are your positive and negative counting numbers, including 0. So these are what you look at when we're talking integers. So natural numbers are these right here. Whole numbers are these right here. And integers are all of those right there. And we'll talk about how they relate to each other here in just a little bit. So we got to be able to graph, on the coordinate plane or on a number line. A point is a coordinate. A graph, you're going to graph 1. That's the graph of 1. That's the graph of -3. You can graph fractions as well. And realistically, what that denominator does is the denominator tells you how many sections you're going to divide that unit up into. So the distance between 2 and 3, or 1 and 2, that denominator is going to tell you that you're going to break it up into 4 segments. So there's segment 1, 2, 3, and 4. So now we've got segment 1, 2, 3, and 4. So if I'm going to do 2 and 3/4, I do 2 and 3 of those. You read a tape measure. If it's 3 and 3/8, you break it up into 8ths. And then you count from there. I don't know if I did it or not, but whatever. But that denominator is the number of places that you break it up into. Now, fractions are what we call rational numbers. So rational numbers are really the quotient of 2 integers. It's a fraction. And again, remember, you can divide by anything but not 0. And so those are considered to be our rational numbers. So when we're looking at rational numbers, you got to keep in mind that the number 20 is a rational number. And it's a rational number because we can write it as a fraction by putting it over 1, for example. Just another couple things. Rational numbers can be written as fractions or expressed as decimals. So 0.5 is a rational number. 0.125 is a rational number, and all of those things. Now, if you create a decimal out of it and that decimal doesn't end, it's what we call an irrational number. So if you take something like pi is approximately 3.14159 ... It goes on and on and on. And this is considered to be irrational because it doesn't end, it doesn't terminate, and it's not repeating. You don't have like 0.33333 and so on. So that's considered to be really what we call an irrational number. So really now we've talked about 5 different sets of numbers. We've talked about rationals, integers, whole numbers, natural numbers, irrational numbers. Now all of these belong to the group of real numbers. Real numbers is kind of this big thing. And then inside of real numbers is all these really different subsets. Now what you have to keep in mind with these subsets is that when you go inside of like the natural numbers, that's your smallest subset. And as you go out, that subset is getting bigger and bigger and bigger. So what that means is that, okay, your natural numbers are just natural numbers. Your whole numbers are whole numbers and natural numbers. Okay, so the whole numbers include 0 plus all of the natural numbers. Integers include all the negative counting numbers plus all the whole numbers and natural numbers. So in other words, if something's an integer, it's also a whole number and a natural number. If something's a rational number, it's also an integer, a whole number, and a natural number. Now, it doesn't go the other way. If something is a whole number, it doesn't mean it's an integer. I'm sorry. Yeah. Okay. If something's a whole number, it doesn't make it a natural number. I went the wrong way. Something's a whole number doesn't mean it's a natural number, because 0 is not a natural number. Integers aren't necessarily whole numbers. They don't have to be. And then you kind of get irrational numbers. And irrational numbers are kind of really their own thing. So one of the things we have to be able to do with these is we need to be able to say what set of each of these they belong to. So if I look at -7, -7 in its kind of its largest set, it's an integer. Okay? So since it's an integer, everything the other direction is what it is as well. So not only is it an integer, but it's also a rational number and a real number. It's all of those different things. For the second one, 3.14, okay, it's a decimal. So a decimal makes it a rational number. So it's a rational number. The next set that it has to belong to then, since it's a rational number, well, if it's rational, that also means it needs to be real. Nothing else, just rational and real. So in a sense, you start at where it's at on that last slide and you can move yourself upward on that slide. You don't go down, you kind of go upward on that slide. If we look at the last one, the square root of 4, well, the square root of 4 is 2. So the smallest set that it belongs to, that's here anyway, it's a whole number. Well, since it's a whole number, it's also an integer, it's also rational, and it's also real. So again, you're going up that line when you're saying which ones they go towards. Yeah, don't worry about that. All right, so the next objective is to find additive inverses, and this should take about 10 seconds. So additive inverses are essentially the opposite of what you are given. If you're given 8, it's -8. If you're given -10, it's 10. The additive inverse is the opposite of it. So the opposite of -1 is 1. That's its additive inverse. The additive inverse of 2 is -2. The additive inverse of -3 is 3, and so on and so forth. When you add additive inverses together, you're always going to get 0. So an additive inverse is just the opposite of what you're looking at. So that brings up this negative symbol and what this means. So that symbol is used to indicate really any of the following: a negative number, such as -9 or -15. The additive inverse, as in -4 is the additive inverse of 4. The other thing it represents is subtraction. A negative and subtraction are really the same thing. Okay, blah, blah, blah. So then we come to of course, absolute value, and being able to determine what absolute value is. Now, absolute value, written in this form, is the distance something is from 0 on the number line. So it's distance, and distance always has to be positive. So absolute value is always positive. So if we look on the number line of -5, -5 is 5 units from 0. So the absolute value of -5 is 5. If we look at 5 itself, 5 is 5 units from 0 on the number line. So the absolute value of 5 is 5 as well. Absolute value is always, always, always going to be positive. Right? So let's look at some examples. So the absolute value of -3. Well, the absolute value of -3 is 3 units away from it. So the absolute value of -3 is 3. Now notice the difference in B between these two, where that negative symbol is. That negative symbol is on the outside, so it has to stay with it. So the absolute value of -3, the negative absolute value of 3 is -3. Same thing kind of with this one. It's the negative of the absolute value of -3. Well, the absolute value of -3 is just 3, so again, our answer is going to be -3. absolute value of 8 plus the absolute value of 1. Well, the absolute value of 8 is 8. The absolute value of 1 is 1. 1 plus 8 is equal to 9. And the last one, notice they're both inside of the absolute value symbol, so you have to do absolute value first. So the absolute value of 7, which is just 7. There's a couple of examples of that. You can also use absolute value to do story type problems. So for example, of the software publisher and fabric mill industries, show which one has a greater rate of change to disregard. So I'm looking at software publishers here and fabric mills here. So the rate of change for this one is 5.3. Now the rate of change for this one says it's negative, but when we're talking about this, it tells us to without regards to the sign. So the rate of change actually there is 5.9. So which one has the greater rate of change? That would be the fabric mills. It's in the negative, but it is a greater rate of change. Last thing then we have to talk about today is inequality symbols and what we do when we deal with inequality symbols. Again, you've done these before. Remember, equations have equal signs. And inequality is when something doesn't equal or greater than or they're not equal. So actually that's an inequality. The ones we're most used to seeing is, kind of the open mouths, so to say. If the symbol is kind of pointed towards the left-hand side, that means is less than. So this reads 8 is less than 9. -7 is less than -16. -8 is less than -2. And 0 is less than -4/3. It's kind of what those mean. If the mouth, so to say, is open to the left, that means is greater than. So we say 13 is greater than 8, 8 is greater than -2, and so on and so forth. Right? So on a number line, just keep in mind that if a number is less than something, it's to the left of it on the number line. If something is greater than something, it's on the right-hand side. And we can use that to determine order. So for example, if we say -9 is less than -2, well, -9 is going to be to the left of 2 on the number line. And you can see that. What symbols mean? Not equal to, is less than, is greater than. If it has a line underneath it, less than or equal to, greater than or equal to. You've seen these before, that's not new. All right, true or false, just quick. -2 is less than -3, that's false. -1 is greater than -9, that's true. 8 is less than or equal to 8, it says equal to, so it's true. And that is false because 12 isn't greater than 12, it's equal to. Okay, so then we have to be able to graph these sets of real numbers. So we want to be able to graph something like x is greater than -2, and we want to be able to do this kind of on the number line. So when we do this on the number line, we're going to use kind of arrows to do this. So this is kind of already done, but I'm looking for all values of x that are greater than -2. So you'll notice that I have a parenthesis here. If it's greater than or less than, you're going to use a parenthesis. If it's greater than or equal to or less than or equal to, you're going to use brackets. Now, you're going to then force your arrow to the direction that you're going to go. So in this case, we want all x values greater than -2. That's why it goes off to the right, because we want to show all values greater than -2. So we can put this in what we call interval notation as well. This is an example of interval notation for x is greater than -2. We want all numbers that are greater than 2, so we're going to use a parenthesis because it's greater than. Our smallest number is -2. Our biggest number is going to be this infinity. And because it's just greater than, we're going to use parentheses. And infinity is always going to use parentheses. So that's interval notation. And that's the infinity symbol. You've seen it before. Parentheses are always used with the infinity symbol. Okay. So if we want to be able to write an interval notation in graph, first interval notation, I look at it and it's that symbol. So I'm going to have parentheses. It says x is less than 5, so my biggest number is 5. The biggest number always goes on the right-hand side. The smallest number always goes on the left-hand side. Well, it goes off forever and ever, so that's negative infinity. Okay, so that's what the solution is for that. If we're going to graph it, here's my graph. There's 0, there's 5. I'm going to have a parentheses, and I have to go less than 5. So parentheses off in that direction is what our graph for that is going to look like. And there's. Okay, interval notation and graph for x is greater than or equal to 0. So it's greater than or equal to this time. So my smallest number is going to be 0. And I'm going to use a bracket this time because it's greater than or equal to. My biggest number this time is it's going to go off to infinity, and infinity is always done with a parenthesis. Okay, so there's that solution, and then the graph, we're going to put a bracket at 0, and it's going off to the right to infinity. All right, so and sometimes the graph sets are between two given numbers. So x could be between 2 and 8. It's called a 3-part inequality. That was loud. And it reads 2 is less than x and x is less than 8. So x is between 2 and 8. So we want to be able to take that and write that in interval notation. Well, when you're doing this in interval notation, your x is going to kind of always be, well, here's our x. We look at that symbol first, and it says x is greater than or equal to -4. So your smallest number is always going to go on the left. Your biggest number is always going to go on the right. Since it's greater than or equal to, that's going to be a bracket. Since this part of it is just greater than, that's going to be a parentheses. So that's your interval notation with that. So that's what our interval notation looks like. If we're going to graph it, we're at -4. We've got a bracket at -4. We've got a parentheses at 2. And it's all of the stuff in between. Now in some books they'll use filled in circles instead of brackets, and they'll use open circles. Ours just uses, it's whatever it uses. They mean the same thing. Okay? And that's what that looks like. And I think that is it for this lesson. A little bit long, I know, but that's going to happen sometimes. Really, what's going to happen in here a lot of times is you're really going to be able to say, I know how to do this stuff, Enertson. I don't need to watch the lesson. I'm going to go right to the assignment, start on the assignment. Boom, 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 boom. I know how to do it. We're good to go. Move on. At least here for the first part of the year. That's going to happen, quite often probably. So you can open up the assignment and say, I'm going to do the assignment, and then maybe work on something else later. If you don't know how to do something, watch the video. It is what it is if you're sitting at home. If you're in front of me, you're probably going to get the lesson anyway, but whatever. It kind of is what it is. So you've got your assignment today. Those of you that are in class, you're going to do it online. Those of you that aren't in class, you're doing it on a PDF inside of Schoology. So have a great one.